Sorry for the long title. Well, first of all, thanks, Elidio and Violetta, for the invitation. It's really a pleasure being here, and the conference has been great. It'll be just outside with my research field, as you will notice from my talk, but I've been learning a lot. So I will be saying some things which are a bit maybe controversial in this audience, but I think that's great. Okay, so in fact, the title of my talk could be this one: where to search, what are the promising environments to search for theories of gravity beyond general relativity. And in fact, my talk, that would be the answer. Like, I will try to convince you, at least, to give you like what we've been learning in the last 10 years within my community of people who do cosmology and modified gravities, that promising places are to look at nonlinear cosmological probes, and that means, for instance, properties of galaxies and clusters of galaxies, to look for screening mechanisms, okay, probing screening mechanisms. And those mechanisms, I will tell you a little bit about it, they are usually embedded in theories of gravity beyond general relativity. Yeah? So, okay, let me start with that. So I'll start with the plot that Kate already showed on the first day, which basically, as you know, so here on the y-axis, we are plotting the curvature. They're like 60 orders of magnitude range. On the x-axis, there's the potential. There's 12 orders of magnitude range. So as Kate said, it's a huge parameter space. And many of the gravity experiments that in this audience we've been talking about, they lie in these regions on the strong field regime. And they have also like tests that we perform on Earth, like with cold atoms to test for modifications for Newton's 1/r R² laws, Etto-Wash experiment. You have lunar laser range, PPN constraints that are coming from the solar system. So all these kind of experiments, they've been performed with very, very high accuracy. And up to now, there's no evidence whatsoever for deviations from general relativity. So it seems that in this region of the parameter space, general relativity works very well. Saying that, I know many of the talks were about testing general relativity in this strong regime. And it would be really nice that we can rule out theories of modified gravity by finding no effects, or even maybe someone gets the ticket to Stockholm and really finds a modification of gravity using, for instance, neutron stars, the black holes merger, etc. But up to now, I think it's not controversial that GR passes very well these kind of tests here in this regime. But we know that these are basically quite small scale, at least for someone like me, a cosmologist, small scale tests. Like they're like systems which have the size of a star or 1 astronomical unit. But we went further than that, and we've been doing tests at megaparsec scales, gigaparsec scales, when we measure, for instance, cosmic microwave background temperature fluctuations using galaxy surveys to go to very high redshift and large scales. And we go to tests in the very weak curvature regime. So we're coming down to this region of the parameter space. And quite strangely, as you all know, it's in this region that we cannot explain what we observe just using some amount of particle physics together with general relativity. It's when we're to plug in dark matter, dark energy. So that's the reason probably that people may say, okay, maybe if there is a modification to general relativity, this modification should be quite strong maybe in this regime of the parameter space. Yeah? So whatever modified gravity is, and if we believe it exists, and might be an alternative to answer to the dark matter or to dark energy, what we know is that at some point modified gravity should recover general relativity, at least in this region of the parameter space. Okay, and the way to recover it, that's what we call a screening mechanism. Okay, so screening meaning hiding. So if there's any modification of gravity, these modifications should be hidden, should be screened away in order to recover general relativity there. Okay, so where to look for modified gravity? Well, we would say, okay, let's look here. You know, do this kind of, keep doing these experiments here in the region of parameter space, because that's where modified gravity lives in. And what I will propose, and you'll see why, is that maybe it's look in this intermediate regime where the screening mechanism appears. And I will try to convince you why that's a nice region, and look at nonlinear, these are nonlinear cosmological structures like galaxies and clusters there. Yeah, okay, so we have seen this plot. It's nice to talk on the last day because lots of people already gave the introduction. So as you know, general relativity, I think you all know, it's quite a unique theory. So if you want to do modified gravity, you have to break one of the conditions for the Love-Loft theorem. Okay? And these conditions basically are how they work. Live in a higher dimensional, your theory is non-local, you have a higher order equations of motions, or you have introduced new degrees of freedom. So there's lots of different types of possibilities of modified gravity. Okay? So we cannot track all of them, but a common feature to all of them is that they should recover GR, at least on the regime that we have been testing, and the tests are very stringent. And the way to recover them is using a screening mechanism. Okay? So we can discuss your preferred theories of modified gravity if they don't have a screening mechanism. And yeah, but I don't have much time for the moment. Okay? So screening mechanism is something that you need if you have a theory of modified gravity. Okay, so let me put a bit more in context and be more specific in order to tell you some tests that I propose, we've been proposing, several people around the world, using galaxy clusters. Okay, so we have to define a little bit of a model. So I'm going to tell you about extending general relativity by adding an extra degree of freedom, a new fundamental field, which is going to be the dark energy field. Okay, so I'm not talking about alternatives to dark matter. Ask me in a coffee break if you want to talk about that as well. But usually when you add a new degree of freedom, what happens is that there's an extra force that appears with particles in our universe, and this basically extra degree of freedom leads to a Yukawa correction to your Newtonian potential. And of course, what happens is that you don't see these Yukawa corrections when you perform tabletop experiments with cold atoms, at a wash, whatever, on Earth, and you don't see this extra degree of freedom with the scalarization, for instance, in neutron stars mergers, black holes, etc. So we don't see this one, and that's why we have then this, again, the screening mechanism. Okay? So the screening mechanism in one slide is basically the following. So let's imagine that we have a Scalar-Tensor theory of gravity, so you introduce this extra degree of freedom, which is a scalar field. It has a kinetic term, a self-interacting potential, and a coupling to matter, to the energy momentum tensor. Okay? And it can have a known standard kinetic term. So let's keep a very general kind of modified theory of gravity. So as I said, you have this Yukawa correction here, which in fact, this is a very simplified one. It's for only standard kinetic terms one, so the Yukawa correction can be something quite complicated like this, okay? But the whole idea is that we do not want to see these Yukawa corrections, and we do not want to see this extra degree of freedom in the experiments that we have done in the upper part of our parameter space. So we want to screen away this degree of freedom. So from the Yukawa correction, one way to do it is basically to have that the coupling to matter is very, very weak. So the coupling to matter that's proportional to Yukawa correction, so if it's a very small number, it goes to zero, so we don't see and we screen away the modified gravity. Another possibility is that the field has a very large mass, it's very massive, so the quantum wavelength is very short, and then it's exponentially damped as well, the Yukawa correction. So that also screens away our field. Or the other possibility, we have basically a large inertia, goes from the standard kinetic term, and that will kill as well the Yukawa correction there. So depending on how you choose, the way you screen away and you hide your extra degree of freedom, you can have different types of screening mechanisms. So you have heard, like probably of the Weinstein screening mechanism, that's going to be related here to large inertia. Then you have, for instance, a Symmetron screening mechanism there. You have chameleon screening mechanisms, you have camouflage. There's a few screening mechanisms, but all of them, in fact, can be classified as three classes. Okay? So that's the way you do it, and this is embedded in the Lagrangian, so it's not something that you put it by hand. So it's a quite nice feature of these theories of modified gravity. And it applies for scalar fields, vector fields, tensor fields like in massive gravity. You know, you can choose what kind of screening mechanism you have to embed in your theory to make it viable. Otherwise, we would have already seen it when we perform experiments or on the form of the gravitational waves that when you receive from black holes merge or whatever. Okay? All right, so I'm just going to give you now just one slide, so one example to tell you how these screening mechanisms work in practice for those who like field theory. So basically, let's look, for instance, at the Symmetron screening mechanism. That's a screening mechanism that we're going to play with the coupling between the scalar field and matter. Okay, so it's just a standard kinetic term with a self-interacting potential, and there's a conformal coupling to matter. Yes? And so if we have the choice of the coupling, for instance, like this, a phi square kind of term, you will change, of course, you'll have a Yukawa correction, a complicated one, not a simplified one. And so what you have is, for instance, that this field will have an effective potential which would like in fact, something very similar to the Higgs potential. So you'll have kind of a phase transition in this field. So for instance, when you have that in very high dense regions, when rho, that's the energy density of matter, which is coupled to the phi squared term, to the field, you will have that the field, the effective potential is just a parabola, so the field will roll out to the minima. So the field will take a vacuum expectation value of 0. And that means that in regions where rho, that's the density, is very high, like for instance on Earth or near a neutron star or black hole, whatever, then the conformal coupling goes to 1 and the field decouples from matter. So there's no Yukawa correction. So this field becomes extremely massive. You can't produce it. It's very difficult to produce it. So you screen away this field in very high dense regions. On the other hand, if the density is very low, for instance, if you go to voids, for instance, of very large scales in the universe, what happens? You have the usual Higgs kind of symmetry breaking. So the field will acquire one of these VEVs. And with these VEVs, the field has a non-zero VEV. And that means that the conformal coupling will become non-zero. And you have a Yukawa correction. So you can say that this phi force, this extra degree of freedom, is not screened, is strong, alive, and kicking, and changing things in our universe. So that's in low dense regions. Okay? So that's the whole main idea of screening mechanisms in usually modified gravity, is that in very low dense regions in the universe, the phi force is very strong, the field is alive, is making changes to, for instance, structure formation in the universe. When you go to high dense regions, the phi force is screened away, or the field becomes very heavy, so you can't produce them, like, again, in strong field events, like we have been talking about here. Okay, so it's a way of hiding these mechanisms. Okay, so, but the thing is, you say, okay, well, there's a phi force in the universe, so probably it will change the clustering of matter universe. So let's look at that. Let's look at how structure formation in the universe changes, okay? So let's compare, for instance, what is structure formation at general relativity and what is structure formation in one of these modified theories of gravity. So I have a F of R theory of gravity, so for those who don't know, it doesn't matter. It's just a modified theory of gravity which has this extra degree of freedom. And there's going to be changes there, okay? So one may think, okay, so let me look then at the matter power spectrum, okay? For the non-cosmologist, the matter power spectrum is basically a way of measuring how much matter clusters in the universe at different scales, okay? So it's something like that, and there are many, many different kinds of measurements, very accurate, especially from the CMB, at the larger scales, but even at small scales with galaxy surveys, we can match the matter power spectrum quite well. So there's lots of observations that put constraints. So the solid line here is basically the GR matter power spectrum. So if there's a phi force, matter should cluster in a different way, and so we should see deviations from the matter class spectrum. And so that's, for instance, what we did. So my talk is going to be about all the plots that I'm going to show you. I should tell you it's about numerical simulations, n-body and hydrodynamical simulations of theories of modified gravity. And my last slide, I'm going to show you some observational constraints. Okay, my last slide, I will tell you. But everything you see is just n-body simulations or hydrodynamical simulations of these theories. Okay, so what we plot here, we did some simulations, for instance, for the F of R gravity. That's the one I'm showing you here. So it's a modified gravity. There's this extra force. And we want to know how much the matter power spectrum, so the clustering of matter, changes with respect to lambda CDM, because there's lots of data, so in principle we could see it. And this is the deviations from lambda CDM, so that's the matter power spectrum. And you see for an F of R model, it can deviate almost up to 40% at this kind of scale. So that's about 1 megaparsec, 2 megaparsecs kind of scale. So that's galaxy clusters kind of scale. So there's a quite big band, and 40% is a lot, it's a big deviation. You see the data points, they fit very well the lambda CDM. So you should say, okay, that's nice, we rule out this model. Let's go for next modified gravity model. Well, life is a bit more complicated because we have, for instance, massive neutrinos in the universe. And when you include those massive neutrinos, you see that all these deviations go down to a point where it's basically very similar to lambda CDM. Okay? So the matter power spectrum, that's a very large scale and very global kind of probe of modified gravity that is very nice. Intuitively, that will be the first place to look at, but there are other particles in the universe, for instance, neutrinos, and that deviates, and that brings down the modified gravity signatures, because, well, massive neutrinos, they have a free streaming length, so they wash out structures at those scales usually. Okay? So we can look at other cosmological probes, for instance, halo abundances. Okay, so in halo abundances, again, this is the plot with respect to lambda CDM, and basically it tells you how many halos you can form in the universe in terms of masses of the halos. So halos with 10 to the 15 solar masses up to 10 to the 13.
And you see that in modified theories of gravity, since there's this fifth force, there's more clustering, so halos are bigger within theories of modified gravity in general. So we could measure then the halo abundances again. We can simulate that. But again, if you put massive neutrinos in there, for instance, you come down to basically what lambda CDM is. So it's very difficult to look at these kind of features when you try to probe exactly just the fifth force at the scales where it could be important. Okay? So we want to look at smoking guns that are not on the modified gravity itself, but on the screening mechanism. And how do we do that? That's what I'm going to try to give an example. Okay? Yeah. So there are a few probes, but I will talk about two of them. One of them is to look at velocity profiles in galaxy clusters. So we have galaxy clusters. Observers can do measurements of how fast these galaxies rotate in the cluster, so the velocity dispersions. And you can imagine that if I have an object, a galaxy in the universe where there is modified gravity, this galaxy will move faster if there is an extra force beyond the Newtonian force. Okay, so you should see an enhancement of galaxy clusters' velocities in theories of modified gravity. But again, this is also degenerate with a bit with massive neutrinos, not a lot, but a little bit. And it can be also degenerate with other models of dark matter. We talked about axion dark matter, self-interacting dark matter, hot dark matter. So just measuring the velocity of the galaxy clusters and see whether they are higher or lower than the usual GR prediction, it won't give you the real smoking gun for the modified gravity. But we can do something, which is measure the profile of the galaxy clusters within a cluster. So let me show you what I mean. So again, these are simulations. So this case is not the FFR model, it's the Symmetron model. So it's a model modified gravity, which has the Symmetron screening mechanism. So what we did is like we divide clusters in masses. So very, very massive clusters with about 10 to the 14, 10 to 14 and a half solar masses, up to small clusters in the universe with around 10 to the 13. Okay, so very massive clusters and very small clusters. Okay, and what we did, we are going to measure the velocity of galaxies in the cluster along the radius of the cluster. So this is the center of the clusters, and this is the outskirts of the cluster. Okay, so the center and the outskirts. And these curves, basically, they show you what's the deviation from the prediction from lambda CDM, from general relativity. Okay? So what you see is that in the center of the cluster, so when you look at what is the velocity of galaxies in the center of the cluster, these deviations from lambda CDM, from general relativity predictions, is basically very small. It's around 0. And when you look at what is the velocity of galaxies in the outskirts of the cluster, deviations can grow quite a lot. Okay? And basically the reason for that, is that in the center of the cluster, the density is quite high. So the screening mechanism starts to become very effective, and the phi force starts to disappear. So the Yukawa correction that you have to Newtonian potential will start to disappear in the center of the cluster. While if you're in the outskirts of the cluster, you start to recover background and density, so you start becoming close to voids, and in these low dense regions, the extra degree of freedom is alive, is kicking, the phi force is strong, and so is pushing galaxies to move very fast. And you can see this kind of behavior that you see there's like 25% deviations when you have very massive clusters, which are quite massive, quite dense. So the screening mechanism is still a little bit present. But as we start to do these kind of measurements to smaller clusters, you start to increase deviations from lambda CDM. So there's like a 40% increase on the predicted velocities of galaxies in clusters for small clusters with respect to lambda CDM. So because smaller clusters are less dense, so screening mechanisms are less important. But the key feature here, the smoking gun for the screening mechanism, is the fact there's always this kind of profile. So as you are in the center of the cluster, deviations are always small, and as you go to the outskirts of the cluster, the deviations increase. So this is something that cannot be mimicked from a dark matter model or from just a pure modified gravity where there's no screening mechanism. So it's the fact that you have a screening mechanism that you see you have no deviations, so galaxies behave just like in general relativity in the center of the cluster, and when you're going to look at properties of the galaxies, well, in this case the velocity, at the outskirts of the cluster, you see there are deviations. So that's the smoking gun there. Yeah. Okay, thanks. Okay, so this is one of the promising smoking guns that I told you about. The other one is a very simple one. Since this is a GR audience, I guess you all know about the equivalence principle better than me. And it's a very nice test by comparing. You know, like in general relativity, gravitational mass and inertial mass, they are just the same. So it would be nice to test the equivalence principle somehow. And if you see violations of the equivalence principle, that would be a signature of modified gravity, something beyond GR. So how do we do that? Well, we try, and we did a lot, equivalence principle tests, solar system, in satellites, etc., and we haven't seen anything else. But it would be nice to do those at cosmological scales. And how do we do that? So at cosmological scales, we need to somehow measure a gravitational mass of an object, and we need to measure the inertial mass of that object, and then compare the two of them. How do we do that? Well, astronomers, they measure masses of clusters, or they infer the masses of clusters. And they have several methods to do that. One of them is a measure, in fact, an inference of the mass of the cluster, which will be, in fact, associated to the inertial mass. And they usually do it by inferring the mass of the cluster to seeing how fast galaxies move around the cluster. So the faster they move, the stronger, the larger is the mass of that cluster. So in modified gravity, in general relativity or Newtonian gravity, it's very simple. The kinematical mass of the cluster, so the mass that we infer from these kinematical methods, is going to be basically proportional to how strong the Newtonian force is. So if there is an extra force in our universe, this extra force will make our galaxies move faster, and so will enhance the kinematical mass that astronomers infer when they do this kind of measurements. So they look at a cluster, they measure the velocity of galaxies in the cluster, and they infer a mass. If there's a modified gravity, this mass should be bigger than what in reality it is. But astronomers, they are really clever people, they have another way of inferring the mass of the clusters, and that's through lensing. And in fact, when you do lensing, you are basically inferring the gravitational mass of the cluster. And that, of course, depends on your theory of modified gravity. So if you are within the context of conformal theories of modified gravity, so there's a conformal coupling between this extra degree of freedom and matter. So I'm not talking about these formal theories. We can talk about that on a coffee break if you want. But if you are in a conformal theory of modified gravity, like the ones that I've been talking up to nowadays, basically due to conformal invariance, as you know, null geodesics are not affected by conformal, from this conformal coupling. And basically the lensing potential is the same as in general relativity. So when astronomers use lensing to probe or to infer what's the mass of a given cluster, the answer they get is independent, it's just a geometrical answer, as independent of your theory of modified gravity. So the test for equivalence principle would then to look at the cluster, infer the mass through lensing, and look at the same cluster and infer the mass through kinetical methods. And if the equivalence principle holds, these two masses should be the same. If there's a theory of modified gravity which breaks equivalence principle, then these masses should be different. Of course, the question is, okay, but how much would they be different? So if I have a theory of modified gravity which satisfies the local constraints, constraints performed on Earth, in the solar system, constraints coming from neutron stars merger, black holes, constraints that satisfy the CMB temperature fluctuations, galaxy survey matter-power spectrum, how much different can these be? And we did, again, some simulations for that. And within these models, again, so what I'm plotting here on the y-axis, that's the ratio between the kinematical mass and the lensing mass. So it's basically a measure of the equivalence principle violation. So it should be around 0 for general relativity. And here I'm plotting with respect to the mass of the clusters, the real mass of the cluster, let's say like the lensing mass. So 10 to the 15 very large clusters and very small clusters. So the gray black lines, that's going to be the simulation from general relativity. For those who don't do simulations, it's never zero, yes, because you would expect, oh, it's really 0, 0. No, simulations have errors. So everything here, basically, you can see there's no equivalence principle violations. So the lensing mass and kinematical mass is the same. But when you look at theories of modified gravity, in this case, I'm just showing you for the F of R gravity, you can see there can be violations quite high, around 60%. So if you can measure, get clusters, usually the very small clusters, where the screening mechanism is not so effective, these very small clusters, you can very, very strong equivalence principle violations there. If, of course, if you go to very heavy clusters, where the density is very high, the screening mechanism is very effective, then you don't see equivalence principle violations there when you compare the lensing mass and the kinematical mass. And again, these models that I'm showing you here, you have such a huge violation of equivalence principle. These are models where you wouldn't see any deviations on them on all the present days probes that we have and tests on modified gravity. So that could be a very nice way of doing that. And again, the smoking gun for the screening mechanism is just not to see a violation of the equivalence principle, but seeing that there will be some clusters in the universe, the smaller clusters, you will see equivalence principle violations, while the large clusters in the universe, you would not see. That would give you the smoking gun for an existence of a screening mechanism. And then what is your theory of modified gravity? Then that's some extra work that you would have to do it. But at least you know there will be something there that screens away modified gravity to GR. So there's another way that astronomers use to infer masses of clusters, which basically using X-ray measurements. So they measure how hot the intergalactic medium gas is. They have a profile, and from that they can infer what's the measurements. And when you do X-ray measurements, basically what you are probing, in fact, is the gas of the baryons, of electrons. Okay, so it's quite different from the ones I told you about, but I will tell you this in a minute. So what happens is that this is the mass of the cluster that holds an hydrostatic equilibrium. So it's the pressure from the baryons in a cluster that holds the gravitational mass. And again, if you have, again, a modified gravity with the extra degree of freedom, what you'll see is this hydrostatic mass should be enhanced because there's a stronger gravitational force going in. So you see that with the mass that you infer from thermal methods should be higher than the gravitational mass, and that will give you also an equivalence principle violation there as well, a test to be used. So there's something interesting here that we can do as well. So I will not show you the equivalence principle violations comparing the thermal mass and the lensing mass. They are similar to the kinematical ones. But there's something here that we can do extra with this kind of observation, is that here I'm measuring the coupling between this extra degree of freedom with the electrons that exist, or the gas that exists in the intergalactic medium gas, the hot gas. While with kinematical methods, I'm measuring galaxies moving around the cluster. And when I'm measuring of the galaxies, I'm not looking at the light of the galaxy. Well, I look at the light of the galaxy, but I'm measuring the redshift of this light. And the movement of the galaxy should be related to the dark matter halo that surrounds the galaxy itself. Okay? Because in these models, so I'm believing in a dark matter particle which creates some halos, and yeah, in these models, yeah? So the kinematical mass, in fact, I'm inferring what's the coupling between this extra degree of freedom and the dark matter particle, while with the X-ray methods, I'm inferring, in fact, I'm probing the coupling between this extra degree of freedom and the baryons. And as you may know, well, or you may wonder the question, does gravity, or does this new extra degree of freedom, does it couple in the same way with dark matter and the baryons or not? You know, there's no reason why it should be universally coupled just like the spin 2 field is. Yeah? So there can be different couplings. And when we can do that, we can use basically comparing the kinematical mass with the thermal mass. So the kinematical mass will be a probe of the coupling to the dark sector, to dark matter particles, and the thermal mass will be a probe to the baryons. And comparing the two of them, we can see whether there's a universal coupling between these extra degree of freedom or not. And we can see this again, just like in these theories of modified gravity with the screening mechanism, that again, at very small clusters with 10 to the 13 solar masses clusters, you can have deviations quite large, around 50 to 60%. Well, again, you have the usual screening behavior that at very massive halos you don't see these deviations. So that will be a way of probing whether there is a universal coupling or not between this new degree of freedom and the standard model particles and this new degree of freedom and the dark matter particle. Now, of course, up to now, everything was just theoretical simulations, but there is some data out there that we can use to put constraints on our theory. And the constraints that I'm showing you here, basically, on the y-axis, that's going to be a parameter for your modified theory of gravity. So that's your, in this case, I'm just showing for the f of r gravity. So that's basically, you can think about it, not the strength, but the range of the phi force in this f of r gravity here. So as it goes to 0, to really small values, we recover general relativity. While here on the x-axis, basically, I'm telling you at what scale we are making these tests and these probes. Okay, so very large scale. So this is going to be cosmological scales, gigaparsec scales, and here are basically tests done in the solar system. And yeah. So our work is these two black lines here. And what we're doing is using kinematical mass, so probing using these violation, equivalence principle violations, comparing the kinematical mass and the lensing mass, so gravitational mass and inertial mass. You can put a bound here, so this is going to be about 1 megaparsec scale, so this galaxy cluster scales here, and using the thermal mass, the bound is a bit, yeah, it's not so good, and it comes there. So, and the way we do it, we basically went to the slow and digital sky survey, because there you can find galaxies and cluster of galaxies where they have measurements for the same cluster of the kinematical mass and the lensing mass and the thermal mass from, well, and also take into account the CENTRA, etc. So we look at different experiments, look at the same cluster, and we compare this. Of course, if you have astronomers and observers in the audience, you'd say, yeah, the error bars are huge. They are. There's lots of complicated baryonic physics, but we can get these kind of experiments. Of course, these kind of bounds. Of course, there are better bounds, as you can see, but they are also at different scales, so it's not so bad. Okay, so this is my summary. So I try to convey you the message that if there's a theory of modified gravity, this theory should at some point recover general relativity. The way it recovers in a dynamical way within the theory usually is by a screening mechanism. There are different types of screening mechanisms, but these screening mechanisms have the general feature that when you come to high dense regions where the curvature becomes very large, you recover general relativity. And these modified theories of gravity, usually the effects are very strong at very large scales in low dense regions as cosmological scales. So one can try to be naive. Well, I think we should try and keep doing large-scale experiments like CMB, galaxy surveys, looking at the Mota power spectrum. Of course, it's always important to try to see if there's any modification of gravity there. But another way is to look at these intermediate scales where you have nonlinear structure formation already from the cosmological point of view. So you form galaxies and clusters of galaxies, because in there you have environments where you have a very dense environment where the screening mechanism is active, and so you have general relativity. And at the same time, in the same system, you have low-dense environments, like, for instance, in the outskirts of the cluster, where the modified gravity should be alive and kicking. So on the same system, you can see there should be differences there. And the predictions that we made from the simulations, they show that these deviations can be very large, even if within the same choice of model parameters, those theories pass all the other gravity tests. Okay, thank you.
Thanks very much, David. Do we have any questions from the audience? Oh, a couple over here. Yeah. I think, yeah, first, yeah.
Thanks a lot for the great talk. I'm curious about more or less general aspects because I'm not introduced to the field. So you mentioned that one of the ways of generalizing GR is to introduce some non-locality. Does it correspond to some exchange-like interaction, like quantizing gravitational field and making a graviton? There's something as quanta of interaction, or?
Well, there are many there are many ways of. So I think this was just a slide that I show from Tessa Baker, in fact, on these these non-local theories. Yeah. So there are many ways of doing modified gravity. As long as you break one of the conditions from the Lovelock theorem, you introduce them. So the way you do that, so you can have introduced functions like R over the operator there, and that will become non-local theory. I'm not sure what you... Do you want me to know what's the exact Lagrangian for that? Or?
I'm trying to understand what non-local means, because to me non-local is something which has character of non-point-like interaction. So
yeah, well, and you break non-localities, so you can have non-causal as well effects and things like that. Yeah.
Okay, thank you.
Yeah.
Okay, yeah, Li Jing, I think was next.
Thank you for the talk. So for your velocity profile, you just showed the inner part is consistent with lambda CDM, and outer part is has deviations. So does that can you observe this deviation if you impose a proper dark matter profile? I mean, is there the degeneracy between this dark matter profile and this deviation?
Yeah. The problem is that the deviation, let me try to show you. That's a good question. I guess you can always fine-tune your dark matter profile in order to give you that, but that will give you in one particular cluster. So what I'm showing you here is, this is not just one particular cluster, so these are like thousands of massive clusters, you know, and the average velocity, internal velocity is very small, it's like general relativity, while the outskirts velocity is very high. So you would need to fine-tune your dark matter profile in all these clusters at intermediate scales to be like that, and maybe smaller clusters you'll have to change the dark matter profile to be like that, and the very massive cluster you'll have to change it like that. So I think it'll be a lot of fine-tuning for your dark matter profile to do that. So I think for the moment, the only way to do this kind of behavior is to have like a kind of a screening mechanism. Yeah. But I guess you might say, okay, but there is a dark matter which we can fine-tune to do all that. Yeah.
Okay, there was another question just up there.
Sorry, I feel like I may have missed the last point you made about observations and its constraints on the predictions of the simulations. When you showed predictions of simulations, you were testing equivalence principle and you're using this, the y-axis was the ratio of these masses minus 1. What do observations say about this plot here?
Yeah, so observations basically, they give, well, observations give me the value for a given cluster. They give me the value for the mass that they infer through a lensing method. And they give you the mass through an X-ray from Chandra, or they give you the mass through a kinematical method. And what we did, we basically did it, okay, yeah, but of course the plot I show you is not this one, that's true, yeah. Yeah. So is this one, yeah. So we plotted here because that was the plot that people used to have. So I'm trying to see what you're asking me. How do you translate this into my other plot? Yeah.
Yeah, there are two y-axes, and I'm just trying to connect those two y-axes.
Yeah. So what it would transmit is this one: is that they would go. So the red line would be ruled out, and we would the blue line would still be viable. Yeah, but would be something around, I would say, 0.2 maybe here at this level, unless. Yeah, but the error bars are quite big. So I wouldn't be able, so the red lines is completely, that modified gravity is ruled out. The f of r 10 to the -5, it's still okay-ish, yeah.
But does the data contain this key trend of decreasing equivalence mass violation as a function of mass?
No, no, because we don't have enough clusters on the data to do that. No, yeah. Sorry, yeah, that was your question, yeah. No, unfortunately, there's not enough clusters, yeah, to do that.
Okay, I think we will probably have to leave more questions for the coffee break. And let's thank David again.